Okay, the next section is on line integrals. There's two sort of versions we'll look at in this section. On top of that, one of the versions has two forms for it. We'll look at line integrals of functions along curves. Then we'll look at line integrals of vector fields along the line integral of a vector field. And then we have the differential form of the line integral. Okay, they're going to be throwing a lot at you with regards to these integrals, and I think it's really beneficial if you know how to form them, how to construct them. Not only that, but it's just hints at the power of these integrals. You can literally integrate anything you can imagine. I remember one of my advisors was working with fractals, and she was integrating over fractal regions and stuff like that. So really the sky's the limit here. All we're doing is kind of combining it with higher dimensions and vectors. Okay? But the sky's the limit, really. There's also different kinds of integrals if you keep on studying. There's like Lebesgue integrals and stuff like that, but we don't worry too much about that kind of stuff. Right, so anyways, 15.2, two types of integrals. First, the line integral of a function over a curve. Okay, so first, a line integral of f over c. And we're going to have, it's going to be just adding to the confusion. We have a kind of a symbol for this. It'll look like this. Okay, but we're generally not going to use that form in order to do our work. Okay, this just represents the line integral of f over c. We're not generally going to be able to work with this. We're going to have to turn it into an integral in terms of t. Okay, so we'll have to do some clever fancy footwork in order to pull that off. We'll have to remember things like what's the arc length of a curve, the arc length of a parametric curve, and what's the magnitude of a vector, that kind of stuff. Okay, so that will add to the confusion, but you'll get used to it. So there's kind of the name of what we're doing, and then there's going to be the working definition where we actually can input things into the integral and then have our answers, right? Okay, so what exactly, can I get a geometric idea of what this thing is? And yes, I can do that for you. Okay, so here's the XYZ space, and we're going to have this curve in the plane for this type of problem. We can also have multivariable types where you have 3 variables, but we're keeping it easy for now. So let's imagine we have some curve in the plane. Okay, so this is some curve C, and we can note C with some vector valued function. So C in general will be some R of t, where R of t is equal to x of t comma y of t. Okay. Okay, and then at every point on this curve we can associate with it this function f of xy. So every one of these, there's an xy there. So we can take any point here and plug it into this function, and we'll get a z value, right? So maybe it goes up to here, maybe then this one's not as high, and then it goes back up, then maybe it's right here, and then maybe it's over here, and then maybe it goes really small, then maybe it goes back up higher, and then maybe here, here, here. Okay, and then we sort of connect the dots. And maybe you get something that looks like that. Okay, so the geometric intuition of what this thing is, what you're doing is kind of finding the area of one side of this curtain, right? So we could break this integral down into its elementary kind of pieces, just like when we did the Riemann integrals, and we had we wanted to find the area of this thing, right? We broke it up into a bunch of little change in x's, and then we could approximate each area on each little segment by taking this length and multiplying it by the height at that particular point, and then we would have these little increments. Change in a sub I, right? So it would be f of x sub I times change in x sub I. And then the Riemann man would run across and kind of put those into a sum, and then we would smooth it out with a limit. This is going to do the same thing over here, except instead of having change in x, we're going to have a little change in arc length. Okay, so change in s. Okay. And we can approximate the area of any of these little sections of the curtain by multiplying, sort of, you take an arbitrary x sub I comma y sub I in this interval, and then plop it into the function, and it gives you a height. So we can approximate the area that I just sort of filled in this here, and I'll call that change in h sub I. We're approximating that area now with f of x sub I comma y sub I times change in s sub I. Okay, so it's a lot like what we did here. It's just instead of change in x, I have a change in s, and this is multivariable. Okay, and then your Riemann man is going to run across and pick up all these change in h sub i's, and we'll take the limit of that as the little change in s's go to 0, and what you end up with is our integral for the line integral of f over this curve c. Right, so it would be this thing here. Okay. The problem with this is, what the heck do I put in? How do I evaluate this, right? Given that you're going to be given a vector valued equation for the curve, or you'll have to create this thing, and you're going to be given this function f of x, y. It doesn't seem like it's enough to figure out this integral and what it is. So the way you're going to accomplish that is to kind of remind yourself what this arc length thing is, okay? And in order to pull that off, I need to maybe do a little side sort of work here. So what is arc length first off? As far as working with parametric curves, and what you could do is kind of take this apart and consider this as a set of parametric equations, right? So you could consider those alone, just x of t and then y of t equals whatever, okay? And then to find the arc length of this curve going from a to b, right? All you have to do is integrate from a to b. It's the integral of the square root of x prime of t squared plus y prime of t squared dt. And this formula is kind of the parametric form of the arc length curve that you were given way back in Calc 2, right? So that would have been the integral of the square root of 1 plus the derivative of f squared. And from there, you can kind of get your hands on this just by doing some substitutions and playing around with it. Okay, but we have this. Okay, what the heck is this thing? Right? What the heck is this thing in relationship to this vector value function? Well, that thing is, well, the parts of it, we have the derivative, so it has something to do with the derivative, right? So r prime of t is x prime of t comma y prime of t. First I have to get the derivative, and then square root of these things squared. What is that? Well, that's just the magnitude of this guy. So if you took the magnitude of r prime of t, that would be the square root of this component squared plus this component squared. Okay, this should be a y. Okay, so in this formula up here, I can rewrite it as the integral from a to b of the magnitude of the derivative of r of t dt. Okay? Okay, so what? Well, what I'm after is a formula basically for ds, right? Because I can rewrite f of xy in terms of t. All I have to do is a substitution using the curve. Okay, I just plug that into there. It's this ds, which is really annoying. I don't know what it is. But what I'm saying is, well, here's s. In order to get ds, I just need to take the derivative of this. Okay, and when you take the derivative of an integral, they're kind of like inverse operations. You go back to the chapter on fundamental theorem of calculus, right? So the derivative of s with respect to t, if I look at the differential, it's just going to be equal to, if you wish, ds over dt, but then multiply both sides by dt. It's just going to be equal to the magnitude. It's the inside part of this thing, right? So the magnitude of the derivative of r of t dt, okay? Which is awesome because now I can rewrite my integral in terms of t. So I could take this and plop it into here, and I'll have a formula in terms of t. So let's do that for our working definition then. For the line integral of f over the curve c, we have, so the name for it here, the line integral of f over the curve c is this thing. But we want to put it in terms of t, right? So it's going to be the integral from a to b of f of x of t, comma y of t, times the magnitude of the derivative of r of t dt. Okay, and this thing being the square root of the component squared. Then you can take this up into higher dimensions with extra variables quite easily. So it's just the same spiel, but now you just tack on one more variable, right? So this would be x of t, comma y of t, comma z of t. And then the magnitude of the derivative of this curve, which will be also in 3 dimensions. So now my curve r of t is, I'll just write x, I'll write it all out. X of t, y of t, z of t. The magnitude of that thing is just the magnitude of the derivative of this thing is just the square root of the components of the derivative squared. So this thing in this setting now is the square root of x prime of t squared plus y prime of t squared plus z prime of t squared, and then dt. Okay. Just like this guy right here, if I did not make that clear, this guy right here is just the square root of x prime of t squared plus y prime of t squared. Okay. Okay, right, so those are our working definitions. Hopefully it doesn't get too confusing in the book when you're reading. Basically this is that is that. Okay, let's look at a problem and see if we can handle this. So this one is a 3-variable type, so number 9. We're evaluating the line integral of f along c, so we have f of x, y, z equaling x squared plus y squared plus z squared. Our curve is given, and later on we're going to actually have to find these curves using the tools that we learned back in chapter 11. Okay, so before that section happens, you may want to go back and review that. I'll try to do a little bit of review, but I have a feeling whatever I do, it's kind of not be enough. But anyways, this time the curve is given. R of t is sine of t, cosine t, 2. So it's a circle located at height 2. Okay, so in space okay. Right, the parameter is going from 0 to pi over 2. Okay, so what do we need? We need to replace the x, y's, and z's with these things, and then we're also going to need this part of it too. So I'm going to have to take the derivative of the r of t. So this would be cosine t, negative sine t, and then 0. Okay. Okay, so the integral of this thing is going to end up being the integral from 0 to pi over 2. And I'm going directly to the working definition of this thing now, doing substitutions into it. Okay, so that ensures that when you're doing the integral, you're integrating over this curve, not just integrating haphazardly in the universe. Okay, it sort of threads the needle, or some way of, you're taking a needle and threading it through this function with this. I don't know, that's too abstract. Okay, all right. So I'm plugging these guys in for x, y, and z. So I'll have sine squared t plus y squared, which is cosine. So cosine squared t plus z squared, which is now 4. Okay, so that's f of x of t, y of t, z of t. Then I need this thing. Okay, so then times the square root of these guys squared. The sum of those guys squared. So the first one, cosine t squared, is cosine squared t. Negative sine t squared is sine squared t. And then plus 0 squared, right, which is just 0. Then dt. Right, so you can use all kinds of the Pythagorean identities. Sine squared plus cosine squared is 1. Okay, so this is 1. And then plus 4 is 5, so I have 5 times the square root of, and again, this guy is 1. 1 plus 0 is 1, so that's just 1. Okay. The square root of 1 is just 1, so you have 5 times 1, which is 5. Now you can factor the 5 out of the integral. The integral of 1 dt then is t, and we're evaluating from 0 to pi over 2. So the answer is 5 pi over 2. Okay, okay, great. Our next section then is to figure out how to generate these curves, right? Because they're going to say, okay, I want you to integrate over a circle or something like that, and you have to figure out this thing. Okay. Okay, so we need a little bit of a review for creating these vector value functions from scratch. And I'll try to get very quickly. I'm trying to find where we first learned how to do that. I think it's 11.5-ish for lines. And then 12.1-ish in general for vector valued functions. So you may want to recall a little bit of 11.5 and then a little bit of 12.1. Okay? So in particular, let's start out with creating vector value functions for lines. So create R of t for the line from 0, 1 to 3, 2. Okay. Okay. So first we taught you how to do this with regards to parametric equations. So in order to do that, we kind of needed one directional vector. And then 2, we needed a point. Okay. And it's very similar to what you did in basic algebra with creating the equation of a line. You need a slope and you need a point. It's the same idea here. Okay, no big deal. Right. So in particular, the way usually the vector is given, but if it's not given, you can create the directional vector just by taking the difference of these two things. Right. So my directional vector in this example is just going to be 2 minus 1 and 3 minus 0. Let's say you do them in reverse for vectors. So 3 minus 0 is 3, and then 2 minus 1, I was trying to find the slope, right? 2 minus 1 is 1. So our directional vector is 3, 1. Okay. And what that means is that our equation of a line has to have, for instance, x values such that when I create a vector from any x value on that line with one of these points, so I'll just take this point here, so x minus 0 has to be a constant multiple of this component here. Okay. So our first component is 3t. And then our second component, y minus 1, has to be a constant multiple of this component here. So it's 1 times t, or t. So y in that case equaled t. Okay? And that would be our parametric set of parametric equations to represent this equation of a line. Okay? So hopefully you kind of remember that. If not, you're going to have to go back and kind of rebuild your brain and remember how to do that. It's not important because, I mean, we want the vector version, right? So the vector version, what you need is a point and the slope, basically. So the vector valued version, R of t, what we do is first form this kind of slope vector, okay, based off of the subtraction. So it'd be 3 minus 0 is 3, and then 2 minus 1 is 1. Okay? And then your starting place is right here. So it's a lot like slope point form. Then your starting place is 0, 1. Okay? And if you were to take this apart, you could generate this, right? So if you look at this, what is this? R of t equals, this is a scalar times a vector, so you just multiply the components and you get 3t comma t plus 0 comma 1. And I made a mistake over here, right? So if you add 1 to the other side, y is equal to t plus 1. Sorry about that. Right? So over here, you're going to get, when I add these together, 3t comma t plus 1. And hopefully at least that kind of convinces you that what I'm doing here is no different than what I sort of did over here. Okay? The parametric version is just kind of a longer version of doing this. You get the same answer. And this is the way we want to approach it, right? So in general, it's kind of like a slope based off of the difference and then plus your starting position. Okay? So that's for the equation of a line. For other types, you may need to look back at 12.1. Evaluate the vector value function. I'm looking for a good question. Sketch the curve represented by the vector value function. Sure. So problems like 31, this is 12.1. They give you a vector value function. They want to know what the heck it represents, right? So cosine of theta, comma, 3 sine of theta. Okay. We're going to have to go in the other direction, obviously, but hopefully this will put you in a bit. This will ground you in reality of what we're doing. All right. So what you do if you want to figure out what this is, kind of eliminate the parameter, right? So you could say x is equal to cosine theta, and then y equals 3 sine theta. And then you're going to take advantage of trig identities in order to rewrite it as an equation in terms of x's and y's. Okay, so this guy over here is y over 3 equals sine theta. And then cosine squared plus sine squared is equal to 1, right? So cosine squared is x squared, and then sine squared is y over 3 squared equals 1. And so what is this thing? This thing is just an ellipse. Okay? So the end result is going to look like this guy here. Okay? Does this kind of bring, hopefully this kind of rings a bell. In general, they'll ask you to do things like create the vector valued equation, for something like a hyperbola. Okay, so they'll be giving it to you in the xy plane and trying to get you to put it into terms of some parameter, right? So maybe this is 1, 1. So x squared minus y squared is equal to 1. Okay, so how would I do that? Well, you would do trig again. Maybe let note x squared equals 1 plus y squared. So let y equal tangent theta, and then x equals secant theta. And that would kind of work via one of the other Pythagorean identities. So hopefully it's that kind of thing from 12.1 that we also need. Okay, let's dive back into where I am in my notes here in chapter 15. So this is now section 2, and what we're doing is going after, so to make this into a vector valued function, right, you would just write r of theta equals tan of theta, secant theta, comma tan of theta. And furthermore, if you have any sort of, just one more example, and then I swear I'll get into the notes. If you have anything like y equals x squared, you could literally turn it into a vector valued equation by just letting x equal itself, or letting x equal t, right? So if x equals t, then y equals what? Well, y will equal t squared. So your vector value function, in that case, r of t, will be t comma t squared. Okay? Okay, and that would be your curve. So these R of t things are the curves that we're after. Okay, so now let's actually get back to work and take a look at finding R of t. Okay, so section 2, finding R of t. Okay, so number 11, where we have, ultimately we were trying to find the line integral of f, which is this x squared plus y squared thing, over the curve C, which is the line segment from 0, 0 to 1, 1. And right now, that's all we want to do is just figure out the R of t function. Okay. So as I showed you in the previous section on building equations of lines, our R of t function, what do we need? So we need kind of a slope, and then plus the starting point. And the starting point is literally just take the components from your first point and put them here as the components for your vector. Okay, so it's just borrow that, put it here. Okay. For this vector here, it's the slope vector. So you're going 1 minus 0 is 1, and then 1 minus 0 is also 1. Okay. The parameter that will get this job done then is from 0 to 1. And you can check it. You can plug in 0 for t, you get 0, 0. Plug in 1 for t, you get 1, 1. So it works. Okay. You probably want to clean it up because we're going to be having to take the derivative of the thing and all that jazz. So, distribute the scalar. You get t comma t, and then plus 0, 0. And then if you add component-wise, you get t comma t. And that's our R of t. Let's try another one. So here's problem 3. If you took Calc 2 with me, you probably saw this one on our last test. We just did parametric equations. Now we're going to write our curves as vector valued equations. And we're going from 0, 0 to 3, 0 to 3, 3 to 0, 3, and then back to 0, 0. Okay, so I basically need 4 equations here. So this will be curve 1, curve 2, curve 3, curve 4. Okay, so for curve 1, I'm going from 0, 0 to 3, 0. So you need your slope vector. So 3 minus 0 is 3, and then 0 minus 0 is 0 times t, plus your initial starting point, 0, 0. Okay, clean it up, and that will be 3t plus 0, which is just 3t, and then 0t plus 0 is just 0. And the parameter in this case will go from 0 to 1. Okay, next, C2, R of t. In this case, so I'm going from here to here. So the slope 3 minus 3 is 0, and then 3 minus 0 is 3. You could use the same parameter t, because ultimately you'll be doing like 4 different integrals. And so it won't matter if you're going from 0 to 1 or 1 to 2. It just won't matter. Okay? But if the book insists, you can adjust this and go from 1 to 2 by simply replacing t with t minus 1. It's kind of just the idea of shifting or doing a translation of a graph of an equation. It's the same idea. Okay, so, but you can always just use t and go from 0 to 1, so long as you're doing different integrals. Okay, so anyways, plus the starting point, which in this case was 3, 0. Then if you have to simplify, what do we have? So 0 times t minus 1 plus 3, and then 3t minus 3 plus 0. And you can check to make sure it works, right? So when I plug in 1, I'll have 3 comma 0. When I plug in 2, I'll have 3 comma 6 minus 3, which is 3, which is 3, 3. Okay, so just make sure it works. C3, so I'm going from here to here. So in this case, 0 minus 3 is negative 3. And then 3 minus 3 is 0. And then this time we use, because the book insists, t minus 2. And then plus the starting place, 3, 3. Okay, so our parameter will be running from 2 to 3 in this case. Okay, so what is this? Negative 3t plus 6 plus 3 is negative 3t plus 9. And then 0 plus 3 is 3. Make sure it works. So I plug in 2, I get negative 6 plus 9 is 3, so that's 3, 3. And I plug in 3, I get negative 9 plus 9 is 0, comma 3, 0, 3. It works. One more. C4. So I have R of t will equal, let's see, 0 minus 0 is 0, and then 0 minus 3 is minus 3. And this time we want to go t minus 3, plus the starting point, 0, 0, 0, 3. And then our parameter is going from 3 to 4. And so our vector value function for this line will be 0, comma, negative 3t plus 9 plus 3. It's negative 3t plus 12. Okay. Okay. Let's look at another one. We'll just do a couple more of these. And then we'll turn to our I think we should do the differential form next for the line integral. Yeah, the book kind of skips it, but we'll just do the differential form next, and then hit the line integrals of vector fields over curves. So it's number 13 now. So the curve this time is a counterclockwise curve. Well, the function they're giving, let me do that first, is x squared plus y squared. And then our curve is counterclockwise around the circle. X squared plus y squared equals 1. And we're traveling from 1, 0 to 0, 1. All right, so I need to find my vector value function for this thing. It's a circle, so you're probably going to be using x as cosine and y as sine. Some variation on that. Sometimes you have to reverse, put sine there and cosine here, or make one negative, stuff like that. So I'm going to suppose my vector value function, you make it r theta, rt, whatever you want. I'm going to suppose it's cosine theta and then sine theta. But I may have to change it, right, depending on the picture. So let's look at the picture. I'm going from 1, 0 to 0, 1 in this direction. So I need to make sure this works. So if I let theta go from 0 to pi over 2, does it work? So cosine of 0 is 1, and then sine of 0 is 0. And then cosine of pi over 2 is 0, and sine of pi over 2 is 1. So yeah, it works. Okay, so how did I know that? Well, I've done enough of these. For you, you're probably going to have to play around with it a little bit and kind of back engineer it. You know. Okay, all right, so that is our vector valued equation for the circle in the first quadrant. Now we're actually going to do the line integral over that curve. Okay, so what do I need to do? I need to sort of get everything in terms of theta. So I'm going to replace f of xy with f of x of theta comma y of theta, which is going to be then x squared is cosine theta squared, so cosine squared theta. and then plus y squared, which is sine squared theta. This is exactly what we did in the beginning of this lecture, right? So then I need that square root thing. So it's really the ds part of the line integral. It's the square root of, so I need the derivatives of these in order to pull this off. So r prime of theta is negative sine theta comma cosine theta. Okay? And so I put that squared. Negative sine theta squared is sine squared theta, plus this thing squared, so cosine squared theta, and then d theta. And I'm going on the from 0 to pi over 2. Okay, so Pythagorean identities say that this is equal to 1, this is equal to 1. So you have 1 times square root of 1. Square root of 1 is 1, so 1 times 1 is 1. So it's just the integral of 1 d theta, which will equal theta evaluated from 0 to pi over 2, which equals pi over 2. Okay, so no big deal. Let's look at another guy. This one a little more complicated with regards to the curve. It's in space this time. Yeah, let me draw out the x, y, and z axes here in green. Okay. And the first curve is going from 0, 0, 0 to 1, 0, 0. Okay, the second curve is going from 1, 0, 0 to 1, 0, 1. And then the third curve is going from 1, 0, 1 to 1, 1, 1. Okay. So in this case, we really don't care about the parameterization values. So going from 0 to 1 every time will work for us because we're going to be doing 3 different integrals, 1 for each curve. Okay. So we need to find the vector valued formulas for those curves. So we'll call this one C1, this one C2, this one C3. So C1, you're just thinking slope plus starting place, right? So r of t equals the slope. So you subtract these two points. 1 minus 0 is 1, 0 minus 0 is 0, 0 minus 0 is 0, t, plus your starting point, 0, 0, 0, and we can use 0 to 1. So t varies from 0 to 1. And simplifying this, it's just, distribute this scalar. So t 0, 0 plus 0, 0, 0 is t 0, 0. We'll also need its derivative for the integral, so we might as well find that now. Its derivative 1, 0, 0. Okay, C2. So again, you find the difference of the points. So 1 minus 1 is 0. 0 minus 0 is 0. And then finally 1 minus 0 is 1. And then we have t plus our starting position, 1, 0, 0. Okay, and then combine these together. Again, we could use the same. T goes from 0 to 1, okay, because we're going to be using a different integral. So it'll be 0, 0 t plus 1, 0, 0, so that'll end up being 1, 0 t. And then we also need the derivative. So 0, 0, 1. And then finally C3, r of t is subtract the points. So 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0, t plus our starting position, which this time was 1, 0, 1. Okay, and then simplify it. Again, we have the same. T goes from 0 to 1. Simplifying this, we have 0t, 0. plus 1, 0, 1, so 1t 1, and then find the derivative, which will be 0, 1, 0. Okay. All right, now we can start worrying about integrating this function over these curves. The function is 2x plus y squared minus z. Okay, I need 3 separate integrals. So the first integral, and I'm going from 0 to 1 on this thing, you need to replace x, y, and z with these x, y's, and z's. Okay, so the r of t equals x of t, y of t, z of t. So x is t, so I plug t in for x, and then x is 0 and y is 0. So these will just be 0. So you get 2 times x, which is now t, and then times the square root of the components of the derivative squared. So 1 squared plus 0 squared plus 0 squared is just 1, and then dt. Okay, so I have the integral basically of 2t dt, which will be 2 squared over 2t squared over 2, which is t squared, from 0 to 1, which is 1. Next, integral from 0 to 1, I'm replacing x, y, and z here with these x, y's, and z's from the from the second curve. So x is 1, y is 0, z is t. So x is 1, so I have 2 times 1 plus 0 squared, which is just 0, minus z, which is now t. So 2 minus t dt. Oops, and I forgot the square root of all that junk squared, but it'll just be 1. 0 squared plus 0 squared plus 1 squared is just 1 again. So in this case, I'll have 2 minus t dt. And then integrating, I have 2t minus t squared over 2 from 0 to 1. So it'll be 2 minus a half, or 4 halves minus 1 half, which is 3 halves. Next, third one, 0 to 1. This time I'm replacing x, y, and z here with these x, y, and z's. So x is now 1, y is t, z is 1. So I'll have 2 plus t squared minus 1, and then times the square root of 0 squared plus 1 squared plus 0 squared is just 1 again, and then dt. Clean up the integrand. So you have 2 minus 1 is 1 plus t squared times square root of 1 is 1. So you just get 1 plus t squared dt. This will be t plus t cubed all over 3. Evaluated from 0 to 1, which is 1 plus 1/3, which is 3/3 plus 1/3, which is 4/3. And then finally, for the end, all you're doing is adding up all those pieces. Okay? So we'll have 1 plus 3 halves plus 4/3, 1 plus 3 halves plus 4/3, which equals 6/6 plus 9/6 plus 8/6, which is equal to 17/6 plus 6/6, which is 23/6. Okay. We have different forms for the, and we want different forms because sometimes it's easier to do the integral in a different way if you have a different presentation. So the other form for the line integral of, well, we need to wait before we get there. Okay, this will be for a line integral of a vector field. So we need vector field integrals first. Sorry about that. So part 2 then, our second type of integral in this section, if that wasn't enough, is the line integral of a vector field over some sort of curve. Okay. Okay. The standard notation for this thing now is going to look like this: the integral of c of f dot t ds. Okay, so that's kind of the notation for it. It's used mainly in physics for figuring out work. But again, you can kind of look at it just solely as a mathematical object and do whatever you want with it, which is kind of more how I would approach it. But the book, talks about work. So let's first recall what work is, and we'll be able to kind of generate at least some sort of intuition about how the formula works and what it is from this definition of work. So recall work, what was it? It's basically the force in the direction of motion times the distance traveled. So maybe I'm pulling a wagon or something like that, and I'm going from point P to point Q, right? And the angle that the handle is making with the horizontal is theta, and so the force isn't in the exact same direction as the travel of the wagon. So to figure out how much force is going in the direction of motion, you have to do a projection, right? So anyways, the work is equal to the magnitude of the force and the direction of travel, which will basically be, I guess, the magnitude of the projection of the force vector onto the PQ vector times the distance traveled, which would just be the magnitude of the PQ vector. Okay? If you do some fancy footwork, and you may have to go back and kind of review all these formulas, this just turns into the dot product of F and PQ. Okay? You probably don't remember those formulas. I don't want to drag them up and give you nightmares, but go back and take a look if you've forgotten and see if you could sort of get that thing. So this thing, this little packet, is kind of what we're going to be adding up as we go through our new integral here. So what this is geometrically, if you insist, is, okay, I'll have some sort of curve in space. So I don't know what it's doing. Maybe it's going like this, and then it's coming back around. You can go real nuts with it, right? Okay, and you imagine this thing is going through a vector field. So inside this space, there's a vector everywhere. So at every position, x, y, z, at this point here, there'll be a vector maybe going like this. At this point here, there'll be a vector maybe going like this. And then you have this curve going through that vector field. Okay, so at every point on this curve, there's also an associated vector, which is that vector from the force field, if you will. There's also a unit tangent vector, right? So if we were describing this curve here with a vector value function, so again, we're going to call C something like R of t, which will equal x of t, comma y of t, comma z of t. We could associate any point on this curve, a unit tangent vector, and this force vector. Okay? And that's kind of what these guys are up here in the formula. Okay? So let's take this particular point here. There'll be a unit tangent vector in the direction of motion. Okay? And the unit tangent vector we can get from this equation here. If you remember, the unit tangent vector t of little t is equal to r prime of t divided by the magnitude of r prime of t. Okay? So there'll be that vector, but there's also the force vector too. So maybe the force vector is going like that. Maybe over here there's the unit tangent vector in the direction of travel, but then there's also this weird force vector doing whatever. So this is the unit tangent vector. This is the force vector. Unit tangent vector, force vector. Okay. And then we could take the dot product at any one of those points. And the dot product will represent part of work, right? Well, it actually equals all of the work. Sort of. Yeah. Did I screw something up? Seems like I screwed something up. Oh, yeah. What we're going to be doing with this integral then is adding up all of these little dot products and then multiplying them by the delta S thing again. Okay, and that will give us little work packets, which I'll call delta W's. I feel like I screwed something up here with the work formula. Just really quick, let me look up the work formula. I'm pretty sure it's a dot product. I just don't use it every day. Okay. I'm more of a math person, a physics person. I don't feel like deriving it for you, so let me just look it up real quick. Where are you? That'd be like chapter 11. Yeah. And we're thinking about work. That would be dot products. So what is work? Yeah, work is the dot product of the force vector with the this vector here. Okay, I see what the deal is. When we create this work increment, so this t isn't exactly like this pq, right? The t in our case is a unit tangent vector. Okay, so you can't just put in f dot t and that will be the thing you're adding up, because that won't represent work, because you're not literally putting in the distance of pq. So to adjust for it, what you're going to do is go f of x sub I, y sub I, z sub I, or x of t sub I, y of t sub I, etc. So I'll just say f of I. You're dotting it with the unit tangent vector, which is kind of a troublesome thing because now it doesn't have the distance that we need for our work formula. Okay, so what you do to kind of get that distance is to tack on multiply by change in s. Okay, so this part will be the distance part for our work formula. Okay, sorry about that. All right, so eventually then what you do is add up all these little work increments and then take the limit to smooth it out, and your formula then is this f dot t ds, okay, which is basically the name for the line integral of the vector field over the curve. Okay. All right. There's other kind of interpretations, but this is kind of what the book does, and so I'm just going to go with what the book is doing. But we need a working definition for this. So, right, I have this, but in general, again, it's kind of the same problem like what we had with the line integral of the curve, the line integral of the function over the curve, right? So I need to kind of get rid of this ds thing and have everything in terms of t, right? And that's going to be kind of using this fact up here of what the unit tangent vector is in terms of r of t. So recall, what is ds? So from the beginning of our lecture, we noted that ds is just equal to the magnitude of the derivative of the position vector, okay, times dt. So I can rewrite the this new line integral. Okay, so we have this new line integral f dot t ds. I can rewrite this as the line integral of f dotted with t. What is t? Well, t is the magnitude of r prime of t. It's r prime of t all over the magnitude of r prime of t times then this thing, right? And hopefully you can appreciate the fact that there's going to be a nice cancellation here. This is a dot product. It's not a regular product, but you can factor constants out of dot products like this thing here, right? So if I dot product this would be in every one of the terms in the resulting sum. So you could factor that out and then multiply this times that, and they would cancel. Okay, so it's it's a little more technical than just saying, well, this divides with this. Well, there's kind of a dot product in here. We have to be careful, but at the end of the day, it is true that that's what's going to happen. So what you'll end up with is this this vector field, which you're going to rewrite in terms of t. So you'll have x of t, comma y of t, comma z of t, and then you're going to dot product that with r prime of t, and then integrate with respect to t, and that'll get the job done. And you're integrating over some t value from t equals a to t equals b. Okay. Okay, so this becomes then our working definition. There's also another way of writing this. This is what we want. Okay. There's another way of writing this, though, that will lead hopefully to maybe another interpretation of this line integral in a different form. And so how do I get my hands on that? Well, it's a matter of just rewriting this thing again. So after I cancel these out, I can rewrite that integral as the integral of f dotted with r prime of t dt. R prime of t, then what is that? Well, that's the derivative of r vector with respect to t times dt, and then you kind of abuse the notation and say, oh, I can remove those, and you end up with f dot dr. Okay, so that's another kind of way of writing this integral. So there's basically three ways here, which adds to the confusion. It's bad enough we have another integral, but on top of that, there's three different ways of writing this integral. Actually four, because we're going to get that fourth way coming up, the differential form, right? Okay, so, right. At the end of the day, there's only two integrals in this section. The line integral of f over a curve C and the line integral of a vector field over the curve C. Okay, that's it. Just all these alternative ways makes it confusing. Okay, so anyways, let's go ahead and take a look at this thing. It's the line integral of f on C, so that's the official title of this. With regards to physics, it's considered the work done by the force field in moving the particle. Okay, so it's physics. It's the work done by the force field and moving the particle. Okay. So let's try one or two or three of these chaps. As my calculus professor would say. Evaluate the line integral of the vector field over the curve. So the vector field here is just xy, and the curve, they're going to give it to you. You don't even have to figure it out. T comma t, and we're going from 0 to 1. Okay. Okay, so it's just a matter of writing up your integral. So I need to replace everything with t's, right? So instead of x, I'm using t. So this is your x of t, this is your y of t, and you're plugging those into here. So I'll have xy is just t comma t, and then I dot that with the derivative of r of t. So r prime of t is 1, 1. So dotted with 1, 1. I'm integrating from 0 to 1, and this is dt. That's it. So the dot product, this times this plus this times this, is t plus t dt. So that's equal to the integral of 2t dt, which of course is 2t squared over 2. So t squared evaluated from 0 to 1 is just 1. And that's your answer. Okay, let's do another. 35. Force field this time is x comma 2y. The curve is t comma t cubed from 0, 0 to 2, 8. And these are given in terms of x's and y's. So we need the t value. C, and this is our r of t. Sorry, smush that in there. Okay, so I need the t value. So you could say, all right, t must be 0, right? So if you plug in 0 for the beginning, you get 0, 0, which is what we want. And then it goes to 2, right? Because you plug in 2, you get 2, 8, which is this point. I also need the derivative, so r prime of t is going to be 1, 3t squared. Okay, and then I go to my integral, which is just the dot product of this, evaluated from 0 to 2. So rewrite f in terms of t's. So x is just t, and then comma 2t cubed, dotted with 1, 3t squared, dt from 0 to 2. Okay. So this will be t plus 6t to the 5th dt. So that's t squared over 2 plus 6t to the 6 over 6, which is just t to the 6, evaluated from 0 to 2. Plug that in. So I get 4 over 2 is 2, plus 2 to the 6, 2 times 2 is 4, times 2 is 8, 16, 32, 64. Answer is 66. Okay, one last section, then the differential form that we use sometimes for the line integral over the vector field. So this is another form for our line integrals of vector fields. And we'll need this later when we look at the other sort of theorems that we'll be encountering. So again, we're given some vector field. Instead of writing, x of t, y of t, z of t, the book is just going to write m, n, and p for x, y, and z. Then your vector valued function, r of t, the curve that we're integrating over, this thing we'll call the x of t, comma y of t, comma z of t. So initially, this isn't, in terms of t. It would just be some sort of, I don't know, so some sort of fourth dimensional surface. And then we later reparameterize it so the integral knows to kind of only integrate the curve part, not the entire part. All right, so our form for the integral over the vector field that we're going to use was that third one, that f dot dr form. Okay. All right, so the three forms, we already saw them. I wrote them down somewhere. I probably lost them in my notes. Oh, here they are. So it would be these. Usually you call it this, but then this is our working definition, and this was another form for the integral over the curve. This is the kind of one we're starting with. Okay. So what is this thing then? This is the integral of the dot product of m and p with the derivative of this thing. So dx with respect to dt, comma dy with respect to dt, comma dz with respect to dt, times dt, right? That would just leave you with the dr part, not the dr over dt. If you sort of abuse notation and distribute this back through, the dt's cancel, you get dx, dy, dz, right? So you can do that dot product then, and what you have is just m dx, because the dt's cancel, and then plus n dy, and then plus p dz. And this thing is the differential form, okay, for the vector field part. This has nothing to do with the line integral of the function over a curve. It's the second type of integral we looked at. Okay. So anyways, let's try to do some of these. And we'll working with evaluating this integral of the vector field with components 2x minus y and x plus 3y. Okay, so this is, if you wanted to, you could back engineer the vector field from this guy. The vector field f is going to be 2x minus y comma x plus 3y. All right. Anyways, number 57. The curve we're integrating over is the line first from 0, 0 to 3, 0, and then the line from 3, 0 to 3, 3. Okay. Okay. So I need to figure out what the heck x and y and dy and, sorry, this should be dx here. I need to figure out what x, y, dx, x, y, and dy are in terms of t. Okay, so I'm going to build vector valued equations in terms of t for these lines. So R1 of t is going to be, as usual, get a slope. So 3 minus 0 is 3. And then 0 minus 0 is 0. T plus the starting position, 0, 0. So my first equation is 3t comma 0. And I can vary the parameter from 0 to 1. And then the second equation, R of t, is going to be 3 minus 3 is 0. And then 3 minus 0 is 3 times t plus 3, 0, the starting place. Okay. And then simplifying, R of t will be 0 plus 3, so 3, and then 3t plus 0 is 3t. Again, I'll vary my parameter from 0 to 1. Okay. So the way I'm going to accomplish this is just literally turning this xyz thing, or in this case xy thing, back in the terms of t. So for the first integral, what do I have? I have x. My x is equal to 3t. I have y. My y is equal to 0. And from these, you can get your dx and dy. So basically, you're doing differentials, right? Like you would do a u sub for your integrals. So dx in this case is 3 times 1 dt. And then dy is just equal to 0 dt. Okay, so I go through my integral and do these replacements. So let's put my integral back. Look at that thing. Okay. So I'll have the integral of 2 times x. So that will be 2 times 3t, which will be 6t, minus y, which is 0, times dx, which is 3 dt. Okay, so times 3 dt, and I'm going from 0 to 1. Plus this other integral, so it'd be x, which is 3t, plus 3 times y, which is 0, times 0 dt. Okay. All right, this thing is just going to cancel out to be 0. So the dy is equal to 0, and when you multiply this big 0 times all of this, this thing is just going to be 0. Okay, over here then I have the integral of 18t dt, and you integrate that and you get 18t squared over 2, which is 9t squared. From 0 to 1 is 9. Okay, next. So now I need to work with the other set of information. Okay, in that case, x is equal to 3, and then y is equal to 3t. Okay, so I need to get my dx and dy. So dx is 0. Dy is going to be 3 dt. And then I just plop everything into my integral. Okay, so I'm replacing x now with 3. So I have 2 times 3 minus y, which is 3t, but then times dx, which is a 0. So this is just going to be 0. Okay? And then plus, and you may think, well, the integral of 0 is a constant. Even if it was a constant, you would just have a constant evaluated from some number to some other number. So it would be the constant minus a constant, which would be 0. So if you're worried about that, any way you slice it, it's going to be 0. Okay. And then plus this integral here. So the integral of x, which is 3, plus 3 times y, which is 3 times 3t, times dy, which is 3 dt. And I'm integrating from 0 to 1. Okay, so in that case, distributing, I'd get the integral of 9 plus 3 times 3 times 3 is 27t dt. And then I go ahead and integrate that. 9t plus 27t squared over 2, evaluated from 0 to 1, is 9. Well, let's go 18 halves, right? So plus 27 halves, which will give me, what is 18 and 27? 5, 1, 45 halves. Okay, and then I have to add that to the other one. So the total answer would be 18 halves plus 45 halves. Because I had a 9 from the other answer. 9 is the same as 18 halves. Okay, plus 45 halves. So 45 plus 18. 8, 9, 10, 11, 13, 4, 5, 6. So 63rd halves. 63 halves. Okay. Okay. Let's look at one more of these and then we'll call it quits. So 59. And the curve is the arc on y equals 1 minus x squared from 0, 1 to 1, 0. Okay. And we're still dealing with the same given integral. Okay. The thing about this is you can actually use x as a parameter, and sometimes that makes things a little bit easier. So you can say, all right, as a vector value equation, let's let x equal x, sorry, as a parametric equation, let x equal x, and then let y equal 1 minus x squared. If you rather, you could just put a t, right? So let x equal t and let y equals 1 minus t squared. But that's equivalent to just saying let x equal x and let y equal 1 minus x squared. So your vector valued equation is in terms of x, right? So you get x comma 1 minus x squared. Okay. But you know, what do we need? We need x, we need y, we need dx, we need dy. You just use this stuff here to get your job done. So x is x, y is 1 minus x squared. Dx then is 1 dx. And then over here, dy is, well, the derivative of 1 is 0, minus 2x dx. And then you're plugging all that information into this form here. Okay? And we're evaluating from x equals 0 to x equals 1. Okay, okay. So let's try it. So I have the integral from 0 to 1 of 2x minus y, which is 1 minus x squared, times dx, which is just dx, and then plus the integral from 0 to 1 of x plus 3y, so x is just x, plus 3 times y, which is 1 minus x squared, and then times dy, which is negative 2x dx. And then it's just a matter of integrating that character. And so what do we have? Let's simplify a little bit. 2x minus 1 plus x squared dx, plus the integral of negative 2x squared minus 6x plus 6x cubed. So negative 2x times negative x squared is 2x cubed times 3 is 6x cubed. You could combine these two integrals. They have the same limits. So this would be the integral of You're not going to get much help out of it, but you can do it. So 6x cubed, negative 6x plus 2x is negative 4x. Whoops, I forgot the x squared. Negative 2x squared plus 1x squared is negative 1x squared, and then minus 1 dx. And then integrate this guy. So 6x to the 4th over 4 is 3x to the 4th over 2. Minus 4x squared over 2 is 2x squared. Minus x cubed over 3 minus x. And then I evaluate from 0 to 1. So this would be 3 halves minus 2 minus 1/3 minus 1. Find a common denominator. So 9/6 minus 12/6 minus 2/6 minus 6/6 is 15 minus 12 is 3. 1/6. No way, really? I screwed something up. Oh, that's a minus there, sorry. 18, 19, 20. Negative 20 plus 9 is negative 11/6. Sorry about that. Okay, that'll do it.